let's think about the linear independence of large sets. So let's suppose that we have k vectors, and they're all in Rn. And suppose that we have lots of vectors k. So in fact, k is bigger than n. So what would it mean? So I guess what we're really asking here is it possible for these to be linearly independent? Well, how would we check that? So to check if it's linearly independent or not, remember we just need to check, are there non-trivial solutions to this equation? So we can form a matrix by putting all the v's in there, and then take our coefficients, right, our scalar coefficients, a1 through ak, set that equal to the 0 vector, and check if there are non-trivial solutions. Right? This is really the matrix version of a1 v1 plus dot 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 up through a sub k v sub k equals 0 vector. So this is the matrix version of this vector equation. Right? And this vector equation is exactly what we need to check to know if these vectors can be linearly independent or not. Okay, so we need to know, is it possible to have non-trivial solutions to this equation? Well, let's see. What would it mean to have non-trivial solutions? Well, to have non-trivial solutions, to have no non-trivial solutions, what would we need from this matrix? Well, to solve this system, we would row reduce it. And to have no non-trivial solutions, that would mean the only trivial solution would be the only solution would be the 0 vector. But what would that look like? I mean, because we have k entries here, right, to force these all to be 0, we would need a 1 in every, we would need a leading 1, a pivot, in every column. Okay, right, because we can't have any free variables. If we had any free variables, then we could choose that variable to be non-zero, and that would give us a non-trivial solution. So to have no non-trivial solutions, we need a pivot in every column. Well, how many columns are there? Well, in this matrix, there's a column for every a, right? Every vector v is a column, but there are k of them, so there are k columns. How many rows are there? Well, there's one row for every entry here. How many are those? Well, right, all of these vectors live in Rn, so that's the number of entries they have. But for a vector, for a column vector, the number of entries is the number of rows. So the number of rows is n. Right, that's also the number of rows in these matrices here. But we assumed that n is bigger, or sorry, we assumed that k is bigger than n. So k is bigger than n, like that. So that means that this matrix here has more columns than rows. So we needed a pivot in every column, but there are more columns than there are rows. That means it's impossible to have a pivot in every column, right? I guess another way to put it is that the rank of this matrix can't be larger than the number of rows. The rank is the number of leading ones, but the most you can have is the number of rows, right? The rank here is less than or equal to the number of rows, which is n, but that's less than k. So you can't have a pivot in every column because you need k pivots, but the most you can have is n, and n is less than k. So this is impossible. We can't have a pivot in every column, and that means it's impossible to have only the trivial solution. So in this situation, to sum up this whole mess, in this situation, there are non-trivial solutions. But that means that all the v's are linearly dependent, right? And that kind of makes sense, you know. We have this idea that linear dependence means that there's some redundancy, or that one of these vectors can be written as a linear combination of the others. Well, if you have more vectors than you have sort of dimensions in your space, then of course one of them has to be redundant, right? If we have Rn, we're used to thinking that, well, n vectors should sort of fill up the space, and if you have more than that, then one of them has to be redundant. So this is pretty intuitive. Just as a quick example of using this, so is this big collection of vectors linearly dependent or independent? So analyzing this in terms of, you know, solving some system of linear equations or row reducing some matrix, that would be a lot of work, because this is a very big vectors and lots of them. So that would be a lot of work. But on the other hand, we have 5 vectors they're in R4 because they each have 4 entries, so we have more vectors than we have entries. So can they be linearly independent? No, they can't be linearly independent. We have too many vectors, so they have to be linearly dependent. Of course, to actually come up with a linear dependence relation, we would need to row reduce the matrix that we get by putting all of these things into a matrix. But just to know that whether they're linearly dependent or independent, we can just look at the number of vectors, right? There are just too many vectors here for them all to be linearly independent. Here's another thing we can do with the idea of linear independence. So suppose that we have a square matrix, so n by n, and suppose that all of its columns are linearly independent. So does that tell us anything about this matrix A? So why don't we name the columns of A, right? Usually we write them like this, A1 through AN. And these columns are linearly independent. So what does that mean? Well, that means if you have some linear combination, how could we write a linear combination of the columns? Well, remember, one clever way to write a linear combination of columns is just to multiply by a vector of scalars, like this. Right, so this whole expression is a linear combination of columns of A. So I guess another way to do this is just to call this capital A times little a. Little a is a vector. So here's a linear combination. And suppose that, so what we know is, because the columns of capital A are linearly independent, this equation has only the trivial solution. Well, if this has only a trivial solution, then that means when you row reduce A, if for a homogeneous equation to have only trivial solutions, that means when you row reduce A, what you get is the identity matrix. And we already know that if you have a square matrix and you can row reduce it to the identity matrix, that means that the matrix is invertible. And in fact, all of these implications go both ways. If you have an invertible matrix, we know you can row reduce it to the identity, but if you can row reduce it to the identity, that means that this homogeneous equation has only trivial solutions. But if this has only trivial solutions, then that means that the columns are linearly independent. So what we have here is an exact correspondence for square matrices. So this is for square matrices only. So if we have a square matrix A being invertible means exactly the same thing as the columns of A being linearly independent. So this actually gives us a nice, up until now we haven't had maybe a firm grasp of why a matrix would not be invertible. But now we see a square matrix is not invertible when its columns are linearly dependent. So, that's something that we understand a little better. So if your columns taken as vectors have some sort of redundancy, then the resulting matrix is not an invertible matrix.